Okay, fine. So good evening to all of you. So if you are having questions, you can start asking, you can express yourself. Are there any questions on the chat? Let me just check. Yeah. So if anybody wants to type in a message, you can also type in. So what is the general feeling about the course? Are you able to understand it? Anybody? Are you finding any difficulties? Okay, Chirag Panchal, course is understandable, but assignment is tough. We have to work hard to solve the assignment. Yes, but the assignment is all based on each of the lecture module, right? So if you actually understand the lecture module, you should be able to do the assignments. See, it is the assignments are not just plain what do you call it? The first level recall knowledge. You may have to think a bit. You have to have understood the concepts. Then, if you think a bit, you will get the answer to the assignments. But it is through the assignments that you will really learn. If you get all the assignments right, you will really learn the power electronic course very well. Any other questions that you would like to ask, Chirag? I have a doubt in the graph of dynamic characteristic of the diode. Yeah. So tell me, what is the doubt that you want to express? Mohammad Khurshid? Yeah, in the transition state, on to off time, current is shown vary, right? So why is that happening? See, when the voltage is shown constant, yeah. So that is the nature of your PN junction. See, when the PN junction is forward biased, so you will see that there is a free flow of the charge carriers, and the potential barrier comes down. But the moment you reverse it, what is the current that you will see? So you will see that the current immediately the diode will not stop conducting, right? So it will take some time for the charge carriers to recombine. So which means it is in the on state only. So but you have reversed the voltage. So once you reverse the voltage, diode is still acting as a short during the transition period, and it is just V by R, whatever R resistance is there in the load circuit, whatever the reverse voltage by R is the current that it will immediately jump to. So that will show that that value will be there till the recombination of the charge carrier starts happening, and gradually it will start decreasing to zero. Pardon me? I am not heard.
So that is a disturbance.
Okay. So, so immediately the current will jump to minus V reverse by R, and it will have initiated the recombination of the charge carriers. So once they start recombining, after some time, you will see that exponentially it starts decreasing the current to zero. So when that exponential fast decrease of the current happens, at that time your voltage will also start building up to reverse blocking state. So that is what you will see. That is basically the nature of a PN junction. It is so even in MOSFETs, it is so even in BJTs, diodes, IGBTs. So there will always be a finite time for the voltage to build up. It will never be instantaneous. What are the losses present in the Schottky diode other than the conduction losses? Any diode, if you take, see, only the doping character, all those things will change, but the diode behavior will still be same. The static and the dynamic characteristic structure will be same. Only the values will be different. So in the case of the Schottky diode, the conduction loss will definitely be very, very less because it has a very low cut-in voltage. And the transition time for it to reach blocking state, reverse blocking state, is also faster because the speed at which the charge carriers will recombine and reach the blocking state is also fast. So that is basically the difference. You will see the losses coming down drastically in the case of the Schottky diodes, or whether it be the conduction and the switching losses. So you will have all the four parts: the on-state loss, the off-state loss, the on to off, off to on. All will be there, only the magnitudes will differ. Yes, it will have reverse recovery loss also. Much smaller than the regular diodes. So Arshit, what type of power converter topology is used in high current power supplies? 100 volts, 150 amps. This is about magnetics and selection now. Switch technology like IGBT and MOSFETs. Yeah, so when you are going to, right now, I think you are not come to that state. We will be discussing another few classes, the isolated converters, bridge converters, so half bridge and the full bridge. So when you are talking of high power converters, especially high current ones, you would go for the full bridge topology. So the full bridge topology is the one which is generally predominant. Most of the power electronics, say beyond 1 kilowatts and all, generally full bridge topology is what is generally preferred. So you will find majority of them in that particular topology segment. Only in the lower voltage side and the lower power side, you will see that single switch, double switch, those type of converters, forward converters, flyback converters, they all will start flourishing more in the low power, in the 500-watt range, that kind of a power deliverance. So the magnetics design also will be dealt with. So you may have to probably wait for some time before we start coming to the magnetics part of it. It will come. You will do the magnetics design of inductance and also design of the various transformers. The full bridge converter topology, the full bridge topology which I just mentioned, has a full bridge transformer for isolation, high frequency transformer, and we will discuss that also in the classes to come. Yeah, Neeraj. Good evening, Neeraj. So right now you probably may be now just entering into the switched mode converters. You may have just finished the linear regulators and starting to go into the switched mode. Today, this one is week 7 or 6. So Nair, is it week 7 or 6
Yeah,
that we have to?
week 7, week 7.
Week 7. So they must have just started about how to do chopping and switching.
I mean, week 7 we are going to upload. I think it is on going on week 6.
Oh, going on is they are not at,
Yeah,
okay, okay. So
yeah,
which
yeah.
means that linear regulator, those things you would be doing. So yeah, you will we will do or we will do all those switched converters. We will do first initially the basic switched converters, primary converters, what we call. Then once you understand that, then we will graduate to the isolated converters, the one which are more practical, and we will also talk about the magnetics also. Please upload solution of assignments. Yeah, we are doing that actually. Actually, after the complete, we upload the solutions after the due date, after all have submitted their their assignments. Imtiaz or Nair, you can add something to that.
Yeah, yes, sir. We are uploaded up to assignment 3. So assignment
Assignment
4.
3. So once the due date is over, we will keep uploading the assignment of that particular one. All the assignments, all the solution manual of the assignment, we will be uploading one after the other. So, so people, have you understood the three-phase rectifier capacitor filter? Or is there any doubts regarding that? Will there be any course on soft switching resonant converters? That is for future only. Yeah, right now it is in this particular in the fundamentals of Voltronics. It will not come. It will probably come in a later advanced version. Some books mention that in forward bias PN junction depletion region height reduces, and some mention width reduces. Please clarify. See, that is basically the way one interprets. See, in some of the books, you will see that the PN junction is drawn horizontal. So you will see the terminals, left and right terminals, and then you will see a vertical junction in the middle. Okay, so the depletion region is seen as a width about the vertical junction. So when you give reverse bias, you will see a change in the width, and when you see the increase in the width, when you see the forward bias, the change is reduced. But some of the books don't talk in terms of this visualization. They talk in terms of energy levels. So the height of the energy band. So that is where you will see some of the books talk of height reduces. When they say height, it is the depletion layer, it is the PN junctions, depletion regions, energy band gap height. So that if once that reduces, you will see a much more freer movement of hole electrons across the junction. So that's what it means. It's basically the perspective what that particular book has. Right? You will have to refer to that book's figure and accordingly match what perspective they are talking. Some books, okay, that is over. No, Chirag, you have written no. No is for what? I think there is a sync problem in the question and answer. You have written no for what? I don't understand.
He's talking about the three-phase rectifier actually.
Oh, okay. I had asked whether any doubts are there in three-phase rectifiers. Okay. Mohammad Khurshid, you are asking. Actually, I faced that question in interview in institution. Okay. That is the question which you talked about. PN junction. Yes. Why does SiC diodes does not have reverse recovery? No. Everything I see, they are high electron mobility transistors. Doesn't mean that it is zero. It is reduced. It is grossly reduced. Never can be zero. No device can have zero. There will always be some capacitance. There will always be some energy storage, and it will have a finite time. So that finite time will be very, very small. SiC also same case. It will be able to reach much higher frequencies than your MOSFETs and IGBTs, but you can never say that the reverse recovery time is zero. Is this course being credited even in your regular college curriculum, or you are taking these courses just to enhance the knowledge, or how is it? What is this one? Is this course falling within the syllabus of your main curriculum subjects? Are you crediting it or something like that one? Or auditing it? Great. Okay. Seven years in industry, taking for enhancement, as in our college or not this much. Okay. Oh, Zirag, so you are working in industry. Which industry? What do you do? Developing street light controllers for smart city. Oh, great. Oh, yeah, you will be using lots of AC to DC, DC controllers, DC, DC converters. Yes, Quantella Inc. Lots of, yes, correct. Great. But this may probably be on the fundamental side. This will be on the fundamental side of the course, not advanced. This is not an advanced course, right? We are going from basics. Yeah, hopefully it is of use to you. Yeah, when we do any advanced course, we will definitely let you know. Which covers all the aspects of it. You want to know? See, I say most of the time I keep telling even my students that the best power electronics book is the data sheets. The data sheets and the application notes of the data sheets. You cannot get better book than that. all other books, see, most of the books will give you the concepts, right? Fine, but they will not give you much on the design aspect. And that is where the whole problem lies. And data sheets and application notes are the best reference material that you can have. So you have to probably go in search of these. They are more accurate, much accurate, and very relevant to that particular circuits that you will be building. When can we expect advanced courses? Yeah, I will let you know as soon as how this course used in e-mobility. Okay. E-mobility, of course, is a different topic. E-mobility has what you call as the E-engine. E-engine means e-propulsion, electric propulsion. So for most of the propulsion, you will find that there is a motor involved. It could be an induction motor, or it could be a synchronous motor, or any one of these special motors like the synchronous reluctance machine or synchronous reluctance machine. Many of these motors are available, which are becoming popular for e-mobility. Now, these motors need to be driven. They need to be controlled, right? They are three-phase machines, and you need a three-phase converters. Three-phase inverters is what we normally would use because they are AC machines. So you will need a DC to AC converters or inverters, as we call, in most of these e-mobility systems. So we do talk of inverters towards the end of this course. At least you will get a feel for the inverters and the way they are done. That is where the connection, you will have to look for connection in the e-mobility. There is also another connection, your DC-DC converters, which you are probably learning here in this course, would also have a connection to e-mobility in the sense of battery charging and smart charging. So that is another connection that you would see in e-mobility. Yeah, so Chirag is saying even this course is very much useful for IoT devices. As for IoT, we use battery calculation for 10 years life and can be useful to choosing the components carefully by calculating power loss being studied 4 phases in first 3 weeks of the course. Yes, yes, of course. See, most of the products, see, once you are in an industry, once you are talking of a product, electronic product, no product will have only one single domain. It will have multiple domains, in interdisciplinary domains connected together. Then only a complete product can be made. So if you take, for example, your battery charger or e-mobility, you will see IoT, you will see power electronics coming in, you will see thermal. Thermal is a very important concept which will come in a big way in most of the power electronic products. How you remove the heat out of the devices, the mechanical aspects of that mounting and the mechanics of that. So this way you will see a lot of other domains also coming into play. So most of the products today are multidisciplinary. So you will see that you will find benefit in one to the other, definitely. So Ashrit is, I'm very much interested to develop resonant and quasi-resonant converters. Where can I start to learn about it from basic? Yeah, resonant and quasi-resonant converters. Yeah, you can. One place is to start with the IEEE Explore. There are several nice papers. You can kind of learn about them. quasi and resonant converters. But only one problem in this quasi-resonant and the resonant converter. Resonant converters especially, they are limited in the sense of they can be used for constant loads, constant applications which demand only constant loads. What happens is that if your load is varying, your Q factor keeps varying, and that can lead to quite a lot of problems, especially in regulation issues in the resonant converters. Quasi-resonant converters, yes, they you can use them. You will have benefits, but they have been used in several of the applications to bring in improvement in efficiency. See, the quasi-resonance find a lot of nice application in zero voltage switching and zero current switching, and that is one of the applications of quasi. Resonant themselves, if you find that your application is a constant load application, then you think of, otherwise you will land in problems. In advanced course, we want thermal stress and electrical stress on devices to calculate device life cycle. Yes, we could do that. You see, in the device life cycle analysis, we used to have detailed separate one course just to calculate the life cycle of the components. But the starting point, you see, when you talk of reliability is a probability figure. It's a probability. You say that it is probable that a batch of electronic products will live for this much amount of time. And most of the electronic components show a particular distribution. It's an exponential distribution. Majority of the electronic components, and some of them may be log normal, but more or less you will see that even in the log normal case, after the initial time period, they all will look like exponential distribution. And that is where the failure rate concept, which is the mean time between failures and those concepts starts coming in. And this failure rate, you need this initial failure rate value for the component, just like datasheet. In datasheet gives the ratings of the components. Like that, the failure rate of the component has to be given by the manufacturer. That data is seriously lacking. So that is where we are not able to actually meaningfully calculate the. Once we have that, then calculating the life cycle becomes much more straightforward aspect. So this failure rate before we used to get from military standards. See, there was this American military standards called the MIL handbook. You may have heard of it, MIL standard, MILSTD, and there are different series, and the latest in that was the 217, F217 series. So even our ISRO, which is launching the space satellites and things like that, they used to use the MIL standards. MIL standards is quite popular. There are also the standards like CNET from France, and you had the British Telecom standards, Belcore standards. These were some of the more popular other standards which were also used for getting that starting failure rate value. But somehow with technology, they have not changed the standard. These standards have not been edited or updated with technology. So what you have the MIL standard values and all for failure rates are 1998. 1998 is the last updation of MIL standard, and AT&T Bell updated their standard only in 2012 or 2011. So after that, so much changes in the technology has happened. So manufacturer does not give readily the failure rate value. Now this starting failure rate value is the parameter that is needed for the exponential distribution. Once that is there, then we can from there do a very scientific analysis on covariate analysis and obtain the estimate of the life of the circuit, whatever the circuit is, based on the electrical and the thermal stresses. So this is the problem which is right now there, and that is why we are actually not able to teach that particular course, because we don't have the starting failure rate values. What are the specialization area in the field of power electronics? Neeraj. Specialization areas means if you want to do research, there are several things you can do in magnetics, you can do in power converters, you can do in multi-level inverters, grid connection, microgrids and grid. See the photovoltaic systems being connected to the grid through power interfaces, battery charging, electric mobility. Someone mentioned electric mobility. No? So the e-propulsion, the battery charging, they are all areas where you need a lot of indigenization and specialization for what is to come in the next 10 years. Which software is used for drawing circuit in the lecture? I use Xournal, Xournal. It is an open source tool, a very nice tool. So that is what I use. But it is, I think, available for Linux. I don't know if it is available for Windows. You may have to check. Oh, it is available. I heard that it is available for from Windows also. Good. So external is very friendly, and you can directly start off using it. And the drawings come very neat, because there is one nice feature in that called the shape recognizer. It as you are drawing, it recognizes the shape, especially simple shapes like rectangle, circle, straight lines, triangle. So it helps a lot. Your drawings become very neat and tidy. Yeah, you can try that. Okay. So any other questions that you would like to ask, or you want to share any information, or you would like to say what should be probable topics that you may want me to cover in an advanced level course? You can tell me now, or you can also let us know in the discussion forum also. Drive circuit design. Yeah, near it. The drive circuit design also is being covered. It is being covered later on in this course. You will see that. Yeah, what I probably will cover is the drive circuit design using discrete components. But today you will see a lot of those circuits that we discussed will be in available in IC form, and there are several ICs readily available for driving the IGBT or driving the MOSFET or even driving the SiCs, which you can use. But internally, the circuits will have one of the topologies that we would have discussed in the course. Yeah, this will come. Drive circuit design will be discussed. Okay, guys, then probably we will meet again. We will meet again sometime in the following month also. And we will keep taking feedback. If you have any doubts, keep telling us. Yeah, Madhavan Ramanujam, could you help me to understand the active front-end converter? Okay. See, active front-end converter is yeah, it's quite popular in the sense that you have active front-end converter which is basically used for making it compatible, making the input compatible to the input supply. So if I am having a sine wave coming from the 230 outlet system, and then you are giving it through your capacitor rectifier filter. So the current is not sinusoidal, definitely, and the power factor is not up to the mark. So what do you do to make it unity power factor? So you use these active devices, active converters. So you can have an active power factor improvement converter at every input, at every interface to 230 volts. Okay, so that is one form of front-end converter where you are having power flow only from the mains to the input, mains to the input of the circuits that will follow. So the mains is converted to DC, but the mains will always see a sinusoidal current which is being drawn. So you will see that it is in unity power factor. So which means that the mains is seeing as though it is a resistive load. Now, if it is capable of bidirectional power flow, in several cases, you would want to put back power into the mains also. Not only draw from the mains, but you also would like to put back the power into the mains. So then we would like to incorporate bidirectionality into the converter. So that is where active front-end converter gets its nomenclature from. So it can actually do both way power direction. I read a lot about design and sizing of inductor transformer, and every designer give theory in different way. So I'm confused. So to design a hardware module of inductor transformer, where should I start? Yes, there are. See, the people see the magnetics is a field where people have different perspectives. People look at it in very many different ways, and that is what leads to those different. See, in several textbooks, literatures, you will see that MMF by reluctance is equal to phi, and that is the Ohm's law. Okay, so the reluctance is treated as like a resistance kind of a thing, but that is not what happens actually. Reluctance is not a lossy parameter. So some others will look at it more like a inverse of a capacitance. So depending upon what model people are using, you will have different roles to play. So in the inductor and the transformer design, there is one concept called the area product concept. So probably it will be good if you can follow the area product concept because it is based on energy conservation principle. So it is much more closer to what is reality. So during making power electronics based applications, mostly timing control required, we do not move ahead due to programming like SCR firing control. What does it mean? Vijay Batu, you are mentioning something about programming. I am not able to get your question. Maybe if you can rephrase it, it will be nice. During making power electronics based application, mostly timing control required. We do not move ahead due to programming. What does it mean? Like SCR firing circuit control. Yeah, I'm not able to understand exactly. If you can rephrase it, then probably I will try to answer that. I'm reading Texas Industry Material for Theory. Is this best for? Okay, and I will not say anything is best. There is no best literature. Texas Industry Material is good. You can do that. It is reasonably practical oriented. There are some application notes which are really good from that. You can definitely benefit from that one. Please do read that. But they will be limiting to mostly the ICs and components available from TI. So that would be the limitation, but still doesn't matter. Concepts are fine. Arshit is asking, is connecting multiple power diodes in parallel is currently a good idea? No, don't do that, because there is no guarantee that the current will share among the diodes connected in parallel. Because if you look at the static characteristic, IV characteristic, you will never find two diodes having exactly the same static characteristic, identical characteristic. It is not possible to have. There will be some deviation. So you will see one of them having slightly lower dynamic resistance. One has a slightly lower dynamic resistance at an operating point, more current will flow. Once more current flows into that, it will the dynamic resistance still reduces further, more, and it will try to hog all the current till it blows, because it would reach the rating. And then after it blows, the next one in the parallel combination will try to hog the current. This is called current hogging, and they will blow, and then in sequence, one after the other, the diodes will blow. So it is not actually a good idea to directly parallel diodes. You can parallel them by putting some impedance in series with the diode, like resistance, but they are lossy. So is connecting, okay. Is possible to cover Arduino based power electronic circuits in this course? No, actually we will the generation of the PWM is left to you. You see, it is not necessary that it should be Arduino based or any particular microcontroller based. It is generic. You can do it using a BSP, or you can do it using a dedicated IC like a TL494, or you can do it using Arduino, or you can do it using some Atmega IC like Atmega 328 or Atmega 32 or even 80 Tiny, one of these things. So that is another part of embedded programming, which will not be part of this particular course. Which other book I should for hardware designing? As I said, hardware designing, you will not see a book as such. You may have to look at data sheets and application notes of that particular components or the switch devices that you use. They are the best hardware designing nodes that you can have. But you've seen the same paralleling of diodes done in welding inverters. See, if you are doing, see in the welding inverters, yeah, it depends upon the topology. You have to first show me the topology of they are done. If they are current controlled, then you can do parallel. If they are voltage controlled, you cannot do paralleling of the diodes. So it depends upon the circuit topology. What if you take directly a diode, and if I have to replace them with parallel diodes, that cannot be done, whichever be the topology. But if I am ORing, what you are talking in welding inverters is ORing of diodes. ORing of diodes can be done because the diodes after ORing will go to a load. So that will limit the current. Whereas in the case of paralleling the diodes, there is no current limiting. So hogging will happen. If I want to design three-phase control rectifier using SCR, that time I am not able to design firing sequence or firing angle of SCR by programming. Why you can do that? It's possible to do today with microcontrollers. You can generate the firing sequence for any SCR converter. See, just like you do firing sequence for PWMs. PWM converters based on MOSFETs and IGBTs. You can do programming even for this. Is it necessary to read programming also? Yes, it is very much important, because today all the control part is in a digital domain. You will use either a microcontroller or a DSP or one of the digital controllers. So knowing C programming, embedded programming is very, very essential. You cannot escape that. You have to do that. Also, you have to do power electronics also. You have to know thermal engineering. You have to know analog signal conditioning to obtain the feedback signals of current and voltages into the digital domain through A to D conversion. So all these are needed. You have to have this knowledge if you have to make a useful electronic product. Yeah, sure. We will have the advanced power electronics course. Yes, we will have that. When to choose GaN SiC devices instead of MOSFET? Is there any specific procedure considering the application? Yes, you see, GaN first thing is cost. MOSFETs are much cheaper, and up to 100 kilohertz operation, you can go in for MOSFETs because that would be a much cheaper solution. Beyond that, the GaN and the SiC have much better mobility and much better frequency response characteristics, and therefore they are faster switches. So you will see the switching losses coming down there. But between GaN and SiC itself, GaN you can use at lower voltage levels. But when you are going at higher voltage levels beyond 1800 volts or 1000 volts, SiC is your only choice. And beyond 100 kilohertz to 1 megahertz, you can go in for GaN or SiC. GaN for low voltage, SiC for any voltage. But by simulation, I can get all answers too. This is for which question? Okay, whichever the question. For programming, you are saying. Okay. No, this is for implementation in the hardware. When you are implementing in a hardware, then you definitely have to know programming. So in the case of the simulation, simulation does not give you all the conditions that are existing in actual practical environment. So it is a much more idealistic environment. It will give you the concept. You can use the simulation like ngSpice or LT-Spice or any Spice or anything, even Simulink, MATLAB Simulink. All these are only concept provers. They will prove a concept and it will probably give you an understanding of that particular circuit. You know what is the waveform that is expected, that kind of thing. But if you go to a practical environment, there are several points. The lines that you draw in simulation in Simulink or simulation, ngSpice or Spice, the lines are inductance free, resistance free, but in the practical situation, there is distributed capacitance, there is distributed inductance all along the track, all along the line. Now, these are practical effects which you will not be able to see in the Simulink, and these have very, very important effects in a particular practical implementation. So unless you practically try to implement your circuits in the lab environment, at least, you will not get the full feel and the insight of that particular circuit. So that is where the programming, that is where I mentioned that programming comes into the picture, because you have to know how to obtain the PWM pulse sequences out of the programs. That is the intent for saying that you need to have programming background, mostly embedded C programming background. What about ANSYS software? See, ANSYS is an environment. You can use that. They are very, very expensive environment. And you have different modules in ANSYS for EMI, for flux, flux path, motor design, all these things you can do, but they are still based on models. And models are the mathematical models inside these simulation environment. And the mathematical models are not representative, or they are only representative, but not the full model of a system, practical system. Nobody can model a full, complete practical system with mathematics, because there are a lot of things that we don't understand, that a lot of things which are non-linear, there are a lot of things which are unmodelable, what you call the unmodeled dynamics, which will be there, which will not go into the maths that represent that system, and which is there in the simulation tool. It can only be, okay, well, you can only compare between two simulation tools and say this is better than that. But the best is the actual practical implementation. That is the most closest you can get to reality. We also use mathematical equations. Yes, you use mathematical equations to arrive at finally some wave shape out of the microcontroller or that digital IC that you will be using, isn't it? So that at the digital IO pin, the signal that you expect, is it correct or not? You know what to expect. Based on that, your program, the mathematics or the arithmetic inside the program, you have the total freedom to change to get what you require. So there, that programming, what you do inside the microcontroller is different from the physics-based mathematical modeling of a system in the simulation softwares. That is different. So what they use in system in the simulation software is trying to estimate the behavior of the system from physics. So that is where the lacking happens. There is a lack of knowledge of the system. We never know fully the system and the nonlinear dynamics that they have. So you try to linearize, and then you are within the bounds of what we know mathematically to represent. But whereas in the case of programming the microcontroller, you are in a well-defined environment. You know what output I want, what is the input that I am getting, and therefore what is the equation I have to use. That is a more closed form like situation. Again, which DSP controller for power electronics? This depends again on the application. If you are doing a very complex application where you need several computation to come, you need to go in for a DSP. Probably the 28XX series from the Texas Instruments is probably something that you can do, but that is at the higher end. Do you really want that kind of overkill for even a small application? So that you have to decide based on the algorithm, based on the number of systems that you are controlling, and based on the length of your algorithm. All these will decide which controller that you would, because you probably may use a DSP controller, but tomorrow another your competitor will come with a simple microcontroller doing the same jobs and function. Then you will lose the market, right? So you have to be very careful in choosing just that controller required. If you go a bit higher, then it will become costlier. Working on WBG driven converter. Should I go deepest? What is WBG meaning? Wide band gap. Is it wide band gap you are talking of? Okay. Wide band gap semiconductors. Which are your GaN and silicon carbide? They also come on that wide band gap. This one. Yeah, again, depending upon the application. Again, I told you, no cost. See, GaN and SiC devices are very costly. So for a low frequency converter, you don't use GaN and SiC, because then your competitor will use MOSFETs and come up with a cheaper solution. So what should dictate finally, ultimately, is your product when it is coming to the market, is it competitive enough? So if it is needed only, you will use GaN and SiC device. And if it is needed for you to go high frequency, remember that as you start going high frequency, switching losses will come down, but your magnetic losses will go up, because the more number of hysteresis loop transitions will happen, and then they become lossy. So which means you should choose coarse magnetic materials which are having less loss or smaller hysteresis loop, which means that they are more costlier. So therefore, you will have to really make compromise between cost and the function, so that you can compete in an open market for a given application. So your application is a driving factor. You will have several solutions, but you have to pick that solution which will match for your application. High frequency planar magnetics. Yeah, planar magnetics is something that you can do for high frequency. The planar magnetic cores are available where you have very very small hysteresis loop area, and therefore the core losses are small at high frequency. But on the other hand, they are costlier than the regular magnetics. So if compactness is the highermost on your mind, or for the application requires, compactness is the one that is most important, and you cannot do without, then you may have to go in for high frequency WBG and planar magnetics. Yeah, you can first learn how to do that, but use that tool, use that weapon only when you need it. No, I will not say that. So I don't need to. No. Don't conclude like that. I said that you should learn what to do, but when the situation, but you should use it only in a situation where it is required. You may have a requirement for high frequency application, then you may have to use that wide bandgap devices. So, but learning is not bad at all. You can learn all these things, but keep them in your toolkit, and when you need it, you will remove it from your toolkit and then use it. So that is how you should visualize. Don't stop from not learning. Don't stop from learning. Okay, guys, then we will conclude now. And thank you all for joining in today. And we will meet again. We will meet again, and hope you enjoy the other week courses that will come in the meantime. Bye-bye.
Okay, sir. I'll end for all, sir.